Hello friends, today we are going to start with our equation of conservation of mass, that is the continuity equation. In aerodynamics, we often come across the many problems involving many unknown quantities. So in order to solve for these unknown quantities, we need to have that many equations. So this equation of conservation of mass will be our first equation to solve for these unknown quantities. Before starting with our equation of conservation of mass, let's start with the Reynolds transport theorem. Actually, all these equations, that is the equation of conservation of mass, equation of conservation of momentum and energy, these are formulated for the systems and not for the control volume or the infinitesimal elements. So in order to apply them, we need to apply Reynolds transport theorem, which says d by dt of mass is equal to the rate at which the mass is accumulated inside the control volume plus outflow, that is the rate at which the mass is going out of the control volume, minus the rate at which mass is going into the control volume. So let's apply this Reynolds transport theorem to our equation of conservation of mass. So this term in the equation of conservation of mass is the rate of change of mass in the control volume, that is the accumulation, as we have talked earlier. And the second term, that is the integration across control surfaces of rho v bar dot n cap dA, is the net rate of flow of mass across the control surfaces. That is, if we take the front and the rear side, then this term is the net rate of flow of mass from front end to the rear end. And the same we can find out about the left hand side, right hand side, top and bottom faces. So we will apply this equation to the small element of size delta x, delta y, delta z. So this is our first term, that is the accumulation of mass inside a small element. We can have delta v, which is the volume is constant, so we can write it as dabba rho by dabba t delta x, delta y, delta z. And the second, we can have net rate of mass flow. Consider the mass flowing left to right. We know that the density at the midpoint is rho and it is changing across this small element. So we'll have the net rate of mass flow at the left face as rho u minus the rate at which the density is changing in direction x into this distance delta x by 2 into the area of the control surface, that is delta y, delta z. And the net rate of mass flow coming out of the right face is rho u plus the rate at which the density is changing is this term, and the distance of right face from the center, that is delta x by 2 into the area dabba y, delta z. So we can formulate the net rate of mass flow, that is the mass outflow minus mass inflow. This rho u will get cancelled and we will get delta by delta x of rho u into delta x, delta y, delta z. Similarly, we can find this thing about the top and bottom faces and front and rear faces. So we'll get these three equations plus the accumulation term, and this all is equal to 0. So in vector notation we can write dabba rho by dabba t plus del operator dot product with rho v bar is equal to 0.